Blanket Metalwork, March 31st, 2019. Today I'm going to do a 3-point bend test, and the explanation is, let me move closer to the sitting, is the length between this point to this point is 84 millimeter. The height from here to here is 18 millimeters. So when this pushed down, bending this bar, then at the break point I will measure the remaining and then subtract the 18 to get the deflection. And that basically we are going to have 440C 63 Rockwell, Aebl 63 Rockwell, Niolox 64 Rockwell, NitroV 61. I did not get the correct hardness I want to be. I like to be 63 or so. And each of these things have the thickness here. So number one thickness here, like for example, so right now what I got loaded is Aebl. Test piece number one. The thickness is 1.88 millimeter. And so, and we use this caliper here to measure the height, whatever left of it after it break. And so I will do one. The sample does jump, so I'm going to zoom in for you to see. Okay, I will do one sample, and then the rest, in the end I will put that spreadsheet there so you can see the result, and also the formula for calculating if you were going to bend it 90 degrees, what would be the length required. And this bend test is slow gradual bend. It's not like a knife and you flex on a piece of wood or something. So, so here you go. This is 63 Rockwell Aebl, 1.88 millimeter thick, and the grid size is not a uniform 220 grid. So I would consider like a more 120. It's not ideal, but it took a long time to prepare this sample. So but when you have a machine testing it, the low rate is a lot slower than what I'm cranking the clamp right now. So okay, this video won't be that long because I'm going to do only one sample, and then I'm going to, in the end, I'm going to give you the compilation. This is History 3.0 that I do. And I chose this hardness because if you were using the for blade and what the edge, how much it can flex. And so there's we talk about edge, lateral edge stability here. So it can flex before it yield. On this case, and first it's going to plasticity, and then after I break this one, I will show you that the sample is slightly bent. I do believe. I will stand back and take a look at how much it's bent. Quite good amount. The break piece will fly. That's why I have this little protection here, the shield. I get impatient. I think I put a low rate a little fast, but that's okay. The band is the function of thickness. So the thinner it is, the more it can flex. I mean, there's a formula for that, so you can calculate. That's why I put thickness for different samples, so that I can calculate, or you can calculate the relative and take thickness into the. Pretty much you divide whatever it is by the thickness, so you take proportion of what it is. It's about to go, I think. Actually, right now is quite a bit of pressure. I mean, I think I should use a bigger clamp, but it's not going to bend like on a neo steel or something, a piece of iron. Yeah, the 3-point, when you have a circular thing, so that you don't have any edges to catch. The same thing for the piston, supposed to be the pressure down. I haven't done many of these, so and I still get a little tentative about it. I think with this much load, I think it will fly pretty hard. I get a little bit concerned now. Not what I haven't done. I will try to not sew and when I do it later on, without on camera, I'm probably going to do a little faster, because this low rate will take too long to do all the sample. Oh. What I do Okay, one thing about the thing is, hopefully, well, as I was talking, got a little bit, I thought it will not make it, break it. The bend, actually they bend right at that curve, one side, right there. That's kind of hard to see, but it's like that. So it's pretty good amount of bend. So it's a lot of pretty good electricity range. I don't think I can fit in, I don't know if let me pull up a little bit. I don't think I can fit in this 3mm remain. So that's for that Aebl. That actually pretty. So I got the 3mm remain. So I got the 15mm deflection. Let me put it 3 here. So basically 3 remain. Bend down from the top. That where deflection would be this thing almost bottom out, because I mean the thickness of the piece is 1.88mm. All right, I'll see you in a bit. All right, I'm back. It took a while to break all these samples, and I recorded the result. And I'm going to, and then this is the, and we go and let's review the summary here of the result. All right. The here different column, and this is the thickness, the T for thickness here. And so for the 440C 63 Rockwell, the first sample is, I mean, you can see here the thickness is number 1 here, the deflection, the thickness, the deflection, and then the angle, how far it bent, and in degree. So for 40C, I mean, you have to deflect for this length, 84mm. It can deflect 7 before it's fracture. In other words, it go beyond yield, and then it go into a little plasticity range, and then it's fracture. And so the second sample is 9. I mean, there is a variation because. Again, as I mentioned, the finish is not consistent, and the dimension is not totally consistent, so that there are going to be deviation, and also the test. I mean, the 3-point angle of pressure difference. So basically, we can look at some sort of like a midpoint or average. That's all you can do. That's how I'm going to take. So it's a 9 for the second one, and a 7 for the third one. And so in other words, this is the how much it can bend in the degree. Aebl, the one in the in the first segment, I mean, in the beginning of the video, is abnormally high bend.
If I look at this, I would say, okay, this something is a little off. So if you have a lot of sample, you want to get rid of the the bias. That means the really high and the really low, because probably, error margin. So for this thing here, and I said, well, this is actually a nice range here. So I could say that Aebl 63 Rockwell. You could, I can pick, maybe reasonable to say it's 12 or 11 and a half if you're conservative. So, but in this case, for this length, 84 millimeter, then it bend, 50, 60 degree, and maybe 11, 60 degree. And that is a lot. And so for Niolox, 64 though, there's a difference in terms of hardness here, 64 Rockwell. And this is, again, one of my top choice in terms of stainless, because again, it's the lateral strength is important to me, because that is that stability. And so for all these numbers in terms of deflection, if I pick the worst one, it's a 9 millimeter deflection. That is a 48 degree at fracture point. The one that when it will explode. And so in that case, and then let's look at, see, for example, down here is how long, what the length of the cord length to be a short length to be so you can bend 90 degrees before it rupture or fracture here. And so in that case, I need 0.115. So if I got 7 inches long, I can bend 90 degrees without fracture. But however, bend 90 degrees doesn't mean an elastic range. It's already entered into plasticity range. That means when you bend it, and then when you straighten it out, it will slightly bend. And so that's what this example for here. And so, but if I take the optimistic range, so I only need 5.6 or so inches to bend 90 degrees. And so that Niolox. NitroV, again, I repeat that, I did not able to achieve the correct hardness, because I would like it to be 63, like Aebl, but there's some, they all heat treated in the same batch. So there's some data, I need to look at, see why it actually got lower hardness. But anyway, I only have 2 of these bars. I got more. Of these bars, I can do another set, even though for the same batch. But because I broke earlier, and also this thing is a little thicker. But you hear the number of thickness here. The thicker it is, it bends less, because again, it's a compression and stretch. The stretch is the one that doesn't support very much, because you can neck in the steel to a certain point, and then it will fracture. And so, but from this 2, and I can say if it's 11, then it would be like say a 58 or or so or 59 degree bend angle. So that a lot more. Even though I'm 61, that's why I said 61 compared to Niolox here. Anyway, you can see all the band, and most of these sample, broke sample, I use harness tester and retested them to make sure that near the breaking point and the bend point, the harness is actually as stated, and actually they are consistent. This is something a little off, so I would say I would think I would toss it out, because it's just when something too good, maybe there's some there's some data a little off. But beyond that, if you were thinking, there are the the two pictures you see of Niolox and Aebl, how much it can bend. I mean, I don't think in the normal course of using the knife, you would want to bend a blade that much. But also, keep in mind though, when you flex, a lot of time the angles are a lot stiffer, and also the point of flex. If you would bend like this, that is not the same thing as this 3-point bending test, because you actually have very narrow where you're holding it. This is 2 point right here and 1 point here, so it's actually a lot shorter length. So the bending angle is more extreme. Keep that in mind when when I discuss these things, because this thing is more control, so you can see what it's like. And anyway, to calculate the degree, it pretty much, you say what is the length, and the short length here, chord length I guess, is 84 millimeter here, and the deflection is how much it deflected. In this case, let's say for this Niolox, it's 10 right here, and then you have the chord length square, and divide by the 8 times the deflection. So this is a standard geometry calculation. Again, I mean, I calculate the A sign, and then I translate from the arc into the degree. Anyways, here's the formula. All right, well, thank you for watching.